Household energy autonomy, the condition where a residence operates independently of centralized utility infrastructure, requires integration across multiple technical and operational domains. The concept differs fundamentally from partial grid supplementation or temporary backup capacity. True autonomy means sustained electrical service continuity regardless of external grid status, weather conditions, or utility company operations. This condition has specific mechanical requirements. Generation capacity must match or exceed consumption loads across all operational scenarios. Storage systems must buffer generation variability and consumption peaks. Consumption patterns must align with generation and storage capabilities. Contingency protocols must address equipment failure, seasonal variation, and extraordinary demand events. These components function as an integrated system rather than independent additions. Historical precedent exists for household energy autonomy. Rural. Electrification in the United States during the 1930s to 1950s included thousands of farm properties operating independent generation systems before grid extension reached remote areas. These systems demonstrated that autonomy was technically achievable with period-appropriate technology, though they also documented the operational demands and failure modes that grid connection eventually displaced. Contemporary interest in energy autonomy reflects multiple motivations: cost reduction, reliability concerns, environmental preferences, or independence from institutional infrastructure. Regardless of motivation, the structural requirements remain consistent. The physics of electrical generation, storage capacity limits, and consumption management necessities operate independently of why autonomy is pursued. The gap between aspiration and implementation typically centers on underestimating system integration requirements. Individual components, solar panels, batteries, generators, are marketed and often perceived as standalone solutions. Functional autonomy emerges only when these elements operate as a coordinated system with appropriate sizing, configuration, and management protocols. I'm James Sullivan. Let's examine how households typically approach energy independence. The most common pathway begins with solar panel installation while maintaining full grid connection. Households install 5 to 10 kilowatt photovoltaic arrays that offset daytime consumption and feed excess generation back to the grid through net metering arrangements. This approach reduces electricity bills but maintains complete grid dependency for nighttime power, cloudy periods, and winter months when generation drops below consumption. Adding battery storage represents the next typical step. Lithium battery banks of 10 to 20 kilowatt hours provide several hours of autonomy during grid outages but remain insufficient for multi-day independence. The batteries charge from solar during the day and discharge overnight or during outages. However, cloudy periods or high consumption days deplete storage faster than solar generation can replenish it, necessitating grid connection for recharging. Backup generators address storage depletion scenarios. Gasoline or propane generators provide on-demand power when both solar generation and battery storage prove insufficient. This creates a three-tier system. Solar is primary, batteries as buffer, generator as final backup. However, generator operation requires fuel availability, mechanical maintenance, and operational attention. The system achieves greater resilience but not true autonomy from external dependencies. Consumption modification attempts to align household energy use with generation capacity. High consumption activities shift to peak solar hours. Energy-intensive appliances operate selectively. Climate control settings adjust based on available power rather than comfort preferences. This approach reduces the generation and storage capacity required for autonomy, but introduces ongoing behavioral demands that compete with normal household routines. Some households pursue phased implementation, installing components incrementally as capital becomes available or as they develop operational experience. A 3 kilowatt solar array expands to 6 kilowatts, then 10 kilowatts. A 10 kilowatt-hour battery bank grows to 20, then 30 kilowatt-hours. Each expansion requires additional electrical work, permitting, and system reconfiguration. The approach spreads costs but extends the timeline to functional autonomy and increases total system complexity. Grid-connected solar systems with net metering achieve cost reduction but not autonomy. When grid power fails, standard solar inverters shut down for safety reasons. They cannot operate in island mode without specialized equipment and configuration. The household loses power despite having functional solar panels on the roof. Converting existing systems to support off-grid operation requires replacing inverters, adding transfer switches, and implementing battery integration, effectively rebuilding the electrical architecture. Battery storage sizing presents persistent challenges. Achieving multi-day autonomy through battery capacity alone becomes prohibitively expensive. A household consuming 30 kilowatt hours daily requires 90 kilowatt hours of storage for 3-day autonomy, plus additional capacity to avoid deep discharge cycling that degrades battery lifespan. At current lithium battery costs of $500 to $800 per kilowatt hour installed, this represents $45,000 to $72,000 in battery investment alone before considering solar generation or other system components. Generator-based backup systems introduce fuel dependency that undermines autonomy goals. A household might achieve electrical independence from the grid while becoming dependent on gasoline or propane supply chains. During widespread disasters or supply disruptions, fuel availability becomes the limiting factor regardless of generation equipment functionality. The system's resilience depends on maintaining adequate fuel storage, which introduces safety considerations, degradation timelines, and rotation requirements. Consumption modification strategies face sustainability challenges similar to behavioral energy conservation. The cognitive load of continuously managing electricity use based on available generation and storage status creates ongoing friction. During multi-day cloudy periods, decisions about which appliances to operate and when introduce stress that degrades quality of life. The autonomy system becomes a source of constraint rather than liberation. Phased implementation encounters compatibility challenges as technology evolves. Solar panels installed in 2020 may use different electrical specifications than 2025 models. Battery chemistries change, inverter communication protocols update. Expanding systems with components separated by years often requires adapter equipment, reduced efficiency due to component mismatch, or premature replacement of functioning but incompatible equipment. The fundamental limitation is that partial approaches to autonomy retain critical dependencies. A system might provide 80% annual energy independence while remaining completely dependent during the 20% of time when grid backup is required. True autonomy demands eliminating all dependencies, which requires comprehensive system design rather than component addition. Energy autonomy system designs exist that prioritize integrated functionality from initial implementation rather than incremental component addition. These formats approach autonomy as a complete electrical architecture rather than modifications to grid-connected systems. One configuration involves oversized generation relative to average consumption, allowing rapid storage replenishment even during suboptimal conditions. A household with 30 kilowatt-hour daily consumption might implement 15 to 20 kilowatts of generation capacity, significantly above typical sizing recommendations. This approach reduces battery storage requirements by minimizing the number of consecutive days the system operates on stored energy alone. Another format category emphasizes generation diversity, multiple generation sources, solar, wind, where applicable, microhydro if geography permits, and continuous electromagnetic or mechanical generation devices operate simultaneously. This reduces dependency on any single generation method and its associated limitations. Solar provides peak daytime power. Continuous operation devices maintain baseline loads regardless of weather or time. The diversified approach stabilizes total system output. Hybrid storage approaches combine battery banks with alternative storage methods, thermal storage for water heating, mechanical storage through pumped water or compressed air for certain applications. This distributes storage requirements across multiple systems rather than solving all storage needs through expensive battery capacity. Consumption infrastructure designed for autonomy differs from grid-optimized households. DC lighting and appliances eliminate inverter conversion losses. High-efficiency systems for heating, cooling, and water heating reduce overall consumption requirements. Load management systems automatically prioritize essential functions during generation or storage constraints without requiring continuous human decision-making. These integrated formats typically require comprehensive planning and initial implementation rather than evolution from grid-connected systems. The design assumes autonomy as the primary requirement rather than treating it as an enhancement to grid dependency. One component format appearing in various autonomy system designs involves compact electromagnetic generation devices that provide continuous baseline power independent of solar cycles or weather conditions. These units typically consist of coil assemblies in specific geometric configurations, operating continuously once installed and connected to system storage. The format integrates into larger autonomy architectures as a continuous generation element. While solar handles peak loads during daylight and batteries buffer short-term variability, these devices address baseline consumption that persists regardless of time or conditions. Installation involves standard electrical connections to battery banks or system distribution panels. The devices appear in system designs distributed as comprehensive documentation packages, including generation sizing calculations, storage integration specifications, and consumption management protocols alongside component assembly instructions. The I format assumes implementation within a complete autonomy framework rather than as a standalone grid supplement. This format represents one configuration approach within the broader category of integrated autonomy systems. Its appropriateness depends on household consumption patterns, geographic conditions, available implementation capital, and individual tolerance for system complexity versus component simplicity. True energy autonomy requires simultaneous attention to generation adequacy, storage sufficiency, consumption alignment, and contingency protocols. Systems addressing some requirements while neglecting others achieve partial independence but retain critical vulnerabilities that manifest during extended adverse conditions. The structural requirements for sustained autonomy remain consistent across different technical approaches and component selections. Generation must reliably meet consumption. Storage must buffer variability. Consumption must operate within system capabilities. Contingencies must address failure modes. Household energy autonomy exists as a technically achievable condition demonstrated through historical precedent and contemporary implementations. The path from grid dependency to functional autonomy involves comprehensive system design rather than incremental component addition, regardless of which specific technologies or configurations are employed.